Right, last video was about exponentials, so this chapter is about logarithms. If you don't know what a logarithm is, then we'll catch you up to speed in just a second. So last video we saw easy exponential equations, something like this here on the left, where we could rewrite both sides to have the same base. And if they have the same base and they're equal, then the exponent has to be the same. So in this case, 49 is equal to, 7 to the power of 2, which means that the exponent over here, x plus 1, has to equal 2, and then obviously x is equal to 1. Something like the equation on the right, however, 48 is not a power of 7, so we can't solve that unless we used graphs. That's true. We could graph that thing and solve it that way. But if we wanted to do it algebraically or get an exact answer, we need to figure out a way to somehow undo this exponential. In other words, we're searching for the inverse of an exponential, and that is something called a logarithm. So you'll notice I skipped section A because it's useless. So here we are in section B, talking about general logarithms. With a base of A, then we say it's a logarithm in base A of B. Okay, and this is the power that A needs to be raised to in order to obtain B. That's a whole lot of words. Let's see it with an example right here. So log base 2 of 8. So what does 2 need to be raised to get us 8? Well, that's obviously equal to 3. So log base 2 of 8 is equal to 3. And in general, you can rewrite any logarithmic statement as an exponential. So we see on the left, it's A to the power of x equals B. And over here, what power does A need to be raised to get B? All right, so it's saying the exact same thing, but this enables us to isolate the exponential and then solve for x. Generally speaking, when we have an equation that has an exponential in it, we want to rewrite it using logarithms. And when we have an equation that has logarithms in it, we're going to want to try to rewrite it using exponentials. So let's practice rewriting things. Down here, can you write an equivalent statement for this one? Log base 10 of 1,000 equals 3. Yeah, that's just 10 cubed equals 1,000. And then 3 to the 4th equals 81. That's wonderful. That means that log base 3 of 81 is equal to 4. Up here in the top right, just a couple things to keep in mind. Our A value here, it's got to be positive. Okay, it can't be 0. Think about that. You're going to have 0 to some power. Well, that's going to be equal to 0. That means x is equal to log base 0 of 0. It means literally any number could be written as log base 0 of 0, and we don't want to really think about that. Except for 0 itself, because 0 to the power of 0 is not defined. But that's a whole other conversation. We also can't have A be a negative number, because if it were negative, we talked about this last time, when we raise it to an even power, it's going to be positive. When we raise it to an odd power, it's going to be negative. And if we raise it to a fractional power, it's often going to be undefined. So we don't deal with negative A's for exponentials. We don't deal with zeros for exponentials. Same thing over here with our logarithms. The A's got to be positive. Also, we don't want A to be equal to 1, because if it was, then 1 to the power of x, that's not really like an exponential shape. That's actually just linear. So we're only dealing with other positive A values. All right. And then we've also got these two kind of identities over here, which at first glance kind of seems like a lot. There's a whole lot of letters happening there, but if you think about it, they make sense, and this enables you to simplify complicated expressions that you might run into at some point. Let's look at this top one here. So we have A to the power of log base A of x. And I claim that that all simplifies to just get you x. And the simplest thing to think about is that a logarithm and an exponent are going to be inverses of each other. So if we have A being raised to a power, that's our exponent, but then I have a log of the same base, that's our logarithm, they cancel out, and what are we left with? Just x. If that's not satisfactory to you, then consider that this logarithm, remember, it literally is the power that A must be raised to in order to get x. And look, we are raising A to that power, therefore it's equal to x. And similarly down below, again, you can think of it in terms of we have a logarithm and then an exponential, so they're going to cancel out, or you can say that we have a logarithm. Remember that a logarithm means this is the number that a must be raised to in order to get a to the power of x. What number must a be raised to get a to the power of x? Well, obviously x. Anywho, here's some simple logarithms that we should be able to work out in our heads. First one, log base 2 of 16. I know that 16 is a power of 2. It's 2 to the power of 4. Secondly, log base 5 of 0.2. 0.2 is a fraction. That's 1/5. So we need to raise 5 to the power of -1. Third one, we have log base 10 of the 5th root of 100. So if it were just 100, then I would know that's 10 squared. So our answer is going to have a 2 in it, but then it's the 5th root. So that means we're going to raise it to the power of 2/5. Then here we have a square root of 2, so that's going to be a 1/2, but it's in the denominator, so we're saying -1/2. And then here we have a very simple logarithmic equation. Solve it for x. Again, we're just going to rewrite it in exponential form. So x is going to be equal to 3 to the power of 5, 243. And before we move on, our little helpful friend from the book tells us that if we don't have a base, that we mean the base to be 10. So often we'll see just an expression like this, log of some number. And this is usually true. So we call base 10 the common logarithm, and it's called the common logarithm due to historical reasons, because way back, like decades ago, so long ago in history, we didn't have calculators that could perform logarithmic operations. So doing logs with a base of 10 was an easy thing to do. There were these devices called slide rules, and like you don't need to worry about that. The point is, it used to be very, very, very common to do work with base 10. So common, in fact, that people got tired of having to write the base over and over again. So they just wrote it as log b. But as with so many things, you need to be careful when you're out there on the internet, children. So here I am at Symbolab. I log of 10. Hit enter. Oh, it tells you that it's 1. And that's what it should be, right? Because 10 to the power of 1 is 10. So I'm expecting log of 10 to equal 1. If I go over to Wolfram and I close this parentheses, what? 2.3? What's going on here? Wolfram Alpha doesn't follow that convention. For Wolfram Alpha, if you don't have a base, they assume that the base is E, and that's because having a base of E is so popular in various areas of mathematics and its applications. So Wolfram Alpha is trying to be, you know, like a math website for the present day, if not the future. So they've coded their site to interpret a log without a base as a base of e. And we'll talk about the base of e in just a couple minutes. We're going to call that the natural logarithm as opposed to the common logarithm. But you can rest assured that for our course, if you do not see a base, the base is 10. Okay, section C now, we've got some of the properties of logarithms that we need to know. And these are not in the formula book, so you need to memorize these. They get used all the time in this course. So first off, if we have a sum of two logarithms with the same base, that's crucial, right? Base of a here, then we can combine them into a single logarithm with the same base where we take the product of the original two numbers. If we have a difference of logarithms, then we turn it into a single logarithm with a quotient. And if we have a logarithm being multiplied by a constant, that constant can be brought into the logarithm as an exponent. Okay, and we often have to use these identities in both directions depending upon what the problem calls for. By the way, you should be able to spot some connections back to exponentials where, you know, when we have the product of two exponentials with the same base, we take the sum of their exponents and we combine them. And when we have a quotient of exponentials, we take the difference of their exponents. So you can kind of see that happening in there. All right, so we should be able to quickly understand what's happening here, right? So here's a sum, it's the same base, base of 10, so it's going to be log of 15. Here's a difference, same base, base of 3, 24 divided by 8 is 3, and then we have log base 3 of 3, which is just equal to 1. And then this one's a little bit tougher. Log base 2 of 5 minus 1. Well, what we can do is we can rewrite 1 as a log with base of 2. So that's what we have here. It's log base 2 of 2. And then take the quotient, 5 divided by 2. There we go. In general, we didn't touch this earlier. If we have the log base a of a, that's always going to be equal to 1, right? Here are three slightly more complicated ones. We now have coefficients to the logarithms. So, you know, we bring the 2 in to make that 7 squared. That's 49. This is going to be 2 cubed. Now that's 8. And now we just have the quotient like before. Same basic thing happening over here. Same thing over there. Here we're actually taking the, we take the exponential out so that we can have the log base, log of 2 divided by log of 2 cancel. So as I said before, we need to be comfortable working our logarithm properties in both directions. In the first two examples, we took a coefficient and brought it into the logarithm as an exponent so that we could simplify. In the last one, we had to take an exponent out of the logarithm and rewrite it as a coefficient in order to simplify. We've got to just do, you know, whatever helps us in that particular problem. All right, and here's just like two more. I got nothing to say about these. Oh, except that to point out, these are show that questions. So remember, in a show that, you don't cross over the equal sign. You just change one or both sides of the equations until they match. Okay, so take a look at that. Make sure it makes sense to you. And then we're going to move on to section D, which is finally, as I mentioned earlier, the natural logarithm. So it's when we have a base of e. That's the only thing that's special about it for us for right now. It's just a number that we will see in logarithms. Other than that, all the rules are exactly the same. We're not adding anything else special into this. So remember those shortcuts that we saw a couple of slides ago. In each of these cases, the ln has a base of e, so I've got a log in base of e raised to the power of 3. The log and the exponential are going to cancel out. It's just equal to 3. Or you could think about it in terms of, look, e cubed is literally e to some number. It's got to be 3. Then the next one over here, we got ln of the square root of e, so that's ln of e to the 1/2. So again, the ln and the e cancel out, and the same thing's happening over there with the last one. These next two slides are just some things we could do on a calculator, I guess. I don't know why you'd ever want to do this, but yeah, if you wanted to write 50 as a power of e, so we're going to use the property we were just talking about like e's and ln's canceling out. So we're going to rewrite 50 as e to the ln of 50. And then we're just going to grab our calculator to figure out what is ln of 50. Oh, it's 3.912 blah, 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 blah. So I guess 50 is equal to e to that power. I don't see how this is possibly useful. Same thing over there on the right, whatever. These are just some easy logarithmic equations. Solve for x. Well, rewrite the logarithmic equation as an exponential. And then ask your calculator, what is e to the power of 2.17 or negative 0.384? And then your calculator will get you an answer. And as we saw in many previous videos, we could also solve these by graphing or by using nsolve, but we don't need to use those techniques here. Okay, then we got properties of logarithms. Look, it's the same stuff we saw before. In fact, some of these examples I think are the same as before. We've just changed the base of the logarithm. So just take a look at these, make sure all these make sense, and you can follow through, but it's nothing new. Okay, I don't really think section E added very much of value, so I'm jumping up to section F here, which is the last property of logarithms. So I said before we saw most of them, but we do have this fourth one, also not in the formula book, and this is the change of base formula. It's really nice, and it always mystified me that it worked when I was a kid. It still kind of does, if I'm being honest. So we've got this logarithm here that for whatever reason we don't like, and we want to change its base to some other base, literally any base that we want. It's really easy. We pick that base, and then we rewrite it as a fraction, where our new base, we see here the same thing in the numerator and the denominator. And then whatever our original base was, that's going to go down here in the bottom, and this number here is going to go in the numerator. So that's how we do change of base. And then this used to be super super important before we had calculators, because if you had something like log base 2 of 9, what you would do is you would change that base into 10, like we have here, and then you could evaluate these two expressions using your slide rule. For us, obviously, like we have a calculator which can perform this directly, so that's how we would do it. However, that being said, there have been plenty of examples on paper 1 in the past where the change of base formula was required. So I'll show you an example right here. This was not from previous exam. However, there was a question on a previous exam that was identical to this. It just had different numbers in it. So let's simplify this gigantic product of logarithms. Now again, it's product of logarithms. It's not a logarithm of a product, so we can't use our logarithmic property to rewrite this as a sum of anything. And even if we could, we don't know what any of these logs are. So what are we going to do? Well, we're going to change a whole bunch of bases. And it doesn't even matter what base we decide to change things to, but we're going to change every single logarithm in here to the same base. I'm calling it A. This could be base 10, could be base E, could be base pi, like whatever base you want, just choose it. Because now, take a look. We've got a log base A of 7 here and here. And a log base A of 9 and 9. And this 11 is going to cancel out with one of the ones over here. And this 13 is going to cancel out with one of those over here. And this log base A of 21 is going to cancel out with one of the ones that was over here. And this log base A of 23 is going to cancel out with one of the ones that was over here. And what are we left with? These two didn't get canceled out with anything. And neither did those. Well, what do we do now? Well, look carefully. 5 and 25, those share something, right? Isn't 25 a power of 5? Oh, and 3 and 27. 27 is a power of 3. This is great. So if we reorganize things just using some basic algebra, we can then use the change of base formula again, backwards, to get two expressions that are easy to simplify. This is just 2 times 3. The answer is 6. I like that problem a lot. I don't like this problem a lot. But let's do it anyway. So this is actually from the textbook. This is a good one, I think. So we want to show that this is equal to 175. So we cannot cross the equal sign. We can't do 2 to the power of 175 and then, or sorry, log base 2 of 175 equals to all this stuff. No, we just need to simplify this left-hand side, because obviously the right-hand side we can't do anything to. So let's just take a look at that exponent by itself. And I don't know, I have no idea how one would think to do this other than just by pure exasperation of like, what else could I possibly do? You've got two logarithms here in the denominators, so you might as well write them to have the same base. It just seems like something that might be productive. So we're changing the base to 10. Again, usually when you use the change of base formula, the base you change into, it's not super relevant, but they're going for 10 here. Okay, great. So next up, we can just do a little algebra. We're dividing by fractions, so we can flip some stuff over. Wonderful. And then my instincts would be to try to get a common denominator here. But rather than multiplying this fraction by log 8 over log 8 and this one by log 4 over log 4, instead, notice that 4 and 8 are both powers of 2. So we can take that exponent out from each of them and give us a coefficient in the front. And then we can simplify it because we've got 4 over 2 and 3 over 3. And now they do have the same denominator already, so that was easier than the other idea, I think. But actually, if you try to add those two fractions together, you get something that it's not really obvious what to do with it, especially when you remember that you still have 2 raised to that fraction. So instead of doing that, what we're going to do is another change of base. Well, first we're going to bring this 2 into the 5 to make that a 25. and then change a base here to get log base 2 of 25, change a base here to get log base 2 of 7. We can then combine those two logarithms using our addition property. And then now it's all going to come together really quickly because that's log base 2 of 175. And now we have 2 to the power of log base 2 of 175. So the exponential and the logarithm cancel out, and we just have 175. I've never seen an exam problem that looked like this. This is a rare example of a book homework question being like, I think, harder than what the IB is likely to ask. But that's a nice exercise to go through. So now we're into section G, which is all about what I referenced back at the very beginning, solving exponential equations using logarithms. Now, for this particular problem in front of us, I would do it not at all what the book does. I don't know, the book is doing something far more complicated than it needs to here. The book is living in the past because they're going to do this all using log base 10. I'll show you what I mean. So we have 2 to the x equals 30. 30 is not a power of 2, so we use logarithms. They're taking the log base 10 on both sides. Okay, that's where we're allowed to do that. And then we're going to take the x, because that's an exponent now, we're going to take that out using that property, and then we're going to divide by log base 2, and then we get this exact answer. X is equal to the log of 30 divided by the log of 2. But we know, if we use a change of base formula, that's just the same thing as log base 2 of 30. And we could get there immediately from here, because if we just write this in exponential form, we know that x is equal to the log base 2 of 30. So I have no idea why they went through all of this work here. I wouldn't do any of that. You can just get immediately to that answer, and that is an exact answer. Log base 2 of 30. I don't, no sense in doing the rest of this stuff. Anyway, part B says to use a calculator to, like estimate what this is. Okay, so even the calculator work that they're showing is, again, using only log base 10. And sure, you could do log of 30 divided by log of 2, and you get 4.91. Of course, we could just use the calculator the efficient way. If we press Control and then this button right here next to the 1, the 10 to the power of x, we will access the logarithm template. We just enter in 2 as the base and 30, and of course, we get the same answer. And by the way, right next to that is the e to the x button, and of course, Control e to the x will get us ln. We can do similar things with e's. You get it? With e's? I didn't even plan that one. We can solve systems. If we want these two exponential curves to meet, of course, you set them equal to each other. And then, it'd be nice if we could get everything maybe to the same side. Because guess what this is going to be? If you predicted a secret quadratic, you'd be right. Yes, if we multiply everything here by e to the power of x, then we get this out, and that's actually factorable. So we know that e to the x is equal to either 1 or 3, which means that x is equal to either ln of 1 or ln of 3. So ln of 1 is equal to 0, as e to the 0 equals 1, and then those are the x coordinates, so we're going to put them back into either of those two equations to get the y coordinates. I guess we should really put it into both to make sure the answers match up. But anyway, those are the coordinates of intersection, and I won't show it, but of course we could check this using technology simply by graphing each of those and then seeing where the graphs intersect. We've gone over that before. You'll just get a decimal approximation for ln of 3. And finally, we've arrived at the end, section H, which is about logarithmic functions. So we saw these way back in the very beginning, and if we consider the logarithm as a single function and the exponential as another function, then what we're getting from this is that f composed of g is equal to g composed of f, which is all equal to x. In other words, as I said earlier, the logarithm is the inverse of the exponential function. Here's an example of exponential decay and exponential growth. It's down below. We can imagine what those would look like if we reflected them over the line y equals x. In a little table here, we know the domain for exponential is all real numbers. That means that the range for the logarithm is going to be all real numbers. We know that the range for the exponential, if it's just a to the x, is going to be y greater than 0. That means that the domain for the logarithm is going to be x greater than 0. We know the exponential has a horizontal asymptote, y equals 0. Therefore, the log has a vertical asymptote, x equals 0. So let's do some stuff with a graph here. So for starters, let's think about function transformations. How can we get from log base 2 of x into this function here, f of x? Well, right here I see a transformation 1 unit to the right and 1 unit up. We can write that as a vector like that. Letter B, domain and range of f. Well, I know that the domain of a normal logarithmic function is going to be x greater than 0. This has been moved 1 unit to the right, so our domain should be x greater than 1. Our range is still going to be all real numbers. Asymptotes. Our normal vertical asymptote is x equals 0, but again, this is moved to the right, so we got x equals 1 is our vertical asymptote. Axes intercepts. Yeah, this will cross over the x-axis, so we can set y equal to 0 or f of x equal to 0, and we can just solve there for solve for x. So we're going to have 2 to the power of negative 1. That's going to be 1/2 is equal to x minus 1, and solving for x, we get 3/2. Putting this all together, we can get a sketch of the graph. Now, what they're doing here is they're just choosing 2 other kind of arbitrary x values. They chose 2 and 5. And the reason they chose 2 and 5 was kind of so that they would get a number in the logarithm that was easy to work with. 2 minus 1 is 1, and you can easily take the log base 2 of 1, and then 5 minus 1 is 4, so you can easily take the log base 2 of 4. So like another number they could have chosen would have been 9, right? But I think that's not really necessary. We've already worked out the vertical asymptote. We've already worked out the x-intercept. I think that's enough information to just draw a sketch of a graph kind of growing in this general direction. And then letter E was asking for the inverse function. So the inverse of the logarithm should be an exponential, and we just do that the same way as we've done before. We're going to switch x and y, and then we're going to solve for y. So we're subtracting 1 over, and then we now have something with a logarithm in it, so we're going to write it as an exponential. We're going to raise 2 to the power of x minus 1, and then get y alone. But we're not going to leave our answer like this. We're going to rewrite it as f inverse of x to indicate that it is, in fact, the inverse of the specifically defined function in this problem, f of x. So that's the story of logarithms, and they show up in a lot of varied applications. Some of these words you've probably seen before. So the way that we measure, starting from the bottom here, the way that we measure decibels for sound uses logarithms. Carbon dating for when we try to get a general sense of how old various artifacts or fossils are. That uses logarithms. The pH scale in chemistry is based on logarithms. The Richter scale for earthquakes, although they don't actually use the Richter scale anymore. They use the moment scale, I think, which is slightly more complicated. But the Richter scale is based on logarithms. Stellar magnitude, how we measure how bright stars are, uses logarithms. And my favorite here is the Weber-Fechner laws, which essentially says, in a nutshell here, that human perception of various things is actually based upon logarithms. In other words, your brain takes in external stimuli and interprets it logarithmically. So 2 quick examples. If you hold out your arm and put a single sheet of paper in your hand, you can feel the weight of that sheet of paper. If you then put another sheet of paper on top of it, you will feel the difference. Right? You'll be able to tell the difference between the 2 weights because it's literally just doubled in weight. However, if you put out your arm and hold a textbook in it and then put a sheet of paper on top of it, you will not be able to notice the difference. You would need many, many sheets of paper put on top of that textbook before you could actually notice in your brain the difference in the weight. Obviously, on a scale, we'd be able to tell, but your brain can't tell the difference. And that's because the single sheet of paper compared to the textbook is proportionally just not as heavy. So if we considered a given weight that you could be holding in your arm, if we then add a particular amount to it, let's call that delta x, the difference in how we perceive the weight, if we look at like the y values here, that difference in how we perceive the weight has gone up by a certain amount. However, if we started off with a larger weight and we add the exact same amount, then the perceived difference in weight ends up being much less. Obviously, this is not drawn to scale, and I just have some random kind of logarithmic curve thrown in there, but you can see what's happening. One more example that you may have experienced in your own life is how human beings experience time passing as we age. And I promise if you haven't experienced this yet, you will as you get older. So let's think about summer vacations, something that you can all relate to. When I think back to summer vacations from when I was in high school, in my memory, those vacations feel like they were about the appropriate amount of time. They feel as though they lasted 2 months or so, and they did, so that makes sense. But when I think about summer vacations now in the present, since I'm lucky enough to have a job that provides me with summer vacations, they feel like they go by in a matter of 2 or 3 weeks. I mean, they start and then they're over again almost immediately. And that's not a complaint. I actually really like what I do for a living, but they still feel much shorter than I know they factually are. And when I think back to summer vacations when I was a child, in elementary school, those summer vacations felt as though they lasted years. I mean, they just went on forever, and it doesn't make any sense, right? Because all of these summer vacations are obviously about the same amount of time. But this is because we tend to experience time as well logarithmically. And again, if you just think about it, for like a 5-year-old, that 2 months of summer vacation is a huge percentage of their life compared to me as someone in their 30s. 2 months is, it is like a blink of an eye almost, and that's how it feels. So the point of all this is to say that, a lot of what we study in this course is very abstract, very theoretical. It can be hard sometimes to see how something might possibly relate to the real world in a manner that's not just like a superficial word problem that's not actually real, because obviously a lot of word problems are kind of just dumb, made up stuff. But here are logarithms, and they really are all over the sciences, and indeed, they are how your brain operates. They are how your brain perceives the world around it. And I think it's valuable for us to understand how our brain works so we can think about our own thinking and about our own experiences in an informed manner.